Welcome to the third lecture of chapter 4. This lecture would be pretty fun. We're basically combining whatever we've learned so far into this lecture by also integrating the redox reaction. So specifically, we will be doing all PCPE type of diagram. As you can guess, this is very, very similar to PCPH diagram. So conceptually would be similar, but we will see how we can integrate E factor instead of H factor into the graph. So we start with constructing the graph, then interpreting some information from the graph, and then making it a little bit more complex and more involved for a system that is more integrated. So before we start today's lecture, just to quickly review what we've learned. We talked about some specific reaction, which we had some, it has some meaning when it comes to type of diagram. So one specific reaction was acid-base reaction with special designation, which was Ka. What else? Complexation. So that was chapter 3, complexation. What else? That could impact speciation. Precipitation. So that could also impact the speciation of specific ion. What else? One more left. Yes, so gas-liquid equilibrium. So that was basically everything. So all of them we talked about, and we know based on chapter 3, the last 2 lectures, how it can be a part of a big diagram. In this lecture, we're going to integrate the redox reaction. So that would be one more branch of the diagram. So to quickly review what we talked about in the previous lecture, we talked about 4 different things. 2 related to half reactions, one at standard, one non-standard, the same thing for redox reaction. And for half reactions, again, to just quickly review what we talked about, we always write it in the standard notation in the oxidation way, which is basically releasing only 1 electron. And for this reaction, we use E0 or PE0, which is at the standard condition. We also talked about the electron activity at non-standard, but by relating it to the standard condition, which was basically the Nernst equation for half reaction. So basically we can estimate the electron activity at any given condition, which is basically a function of the ratio of the oxidized versus the reduced species. We also talked about the full redox reaction. Logically very similar to half reaction. Here, a standard redox reaction is a combination of 2 standard half reaction. So something general like this one that we dealt with in the previous lecture. And we mentioned that if it is a standard redox reaction, then we could relate the standard electron activity of the reaction to the individual oxidation and the reduction. So this is all about the standard condition again. For non-standard, we basically, it relates to the standard condition plus the reaction quotient. We also talked about whether a reaction is spontaneous. So for a spontaneous reaction, which we know delta G is negative, delta G of reaction is negative. We show that this means PE of reaction is also negative. And based on the last line, we had one example that shows whether, for example, this specific species could reduce or oxidize another species. So We did that for standard condition, but we can do it also for non-standard. So today we're going to use what we've learned and basically construct a PCPE diagram. And the whole lecture would be based on 3.5 examples. So not much to talk about, but talking about the examples. So no surprise, PCPE diagram are very similar to PCPH. The only difference might be we have a good sense of what is the range for pH, normally from 0 to 14. And we know, for example, below 7, it's acidic, higher than 7 is alkaline. But for E is a little bit vague. We don't have that threshold of this is like low electron activity, high electron activity. Most of the time, the range will be given. So for example, they say go from PE of 15 to 45. So that's the tiny difference there. Also, just practice to look at electron as a species. So we had for pH, we had H+. It was always dictated by H+. Here, one of the species is electron. So we're treating that as a species, like other species. So the only thing is, as you'll see, some of this speciation is pH dependent. And for this lecture, we'll fix the pH. So it's not talking about, we're not modulating the pH also. It's just fixing the pH, just changing the concentration activity of the electron. So we start from the simplest scenario, going for like one standard redox reaction and see how the PC-pH diagram look like. So let's assume we have the total value of iron to be 10 to the minus 4. We're assuming no complexation, no precipitation, no acid base, nothing, just the redox reaction. And that redox reaction, it's not leaving the system, obviously, because there's no precipitation, it's not evaporating. So this would be sort of a closed system kind of approach for this one. And based on the information that is given, it seems we're going between Fe3 plus and Fe2 plus. And to be able to use this parameter, we have to write the reaction in the standard notation. So that means oxidation and releasing one electron, which in this case is the case. So in this case, K would be equal to E0, like any other expression. Instead of activity for this lecture, we're going with concentration. So it would be the concentration of the product, again, treating electron as a species, and then the reactant. So now we want to see how speciation would change as a function of the activity of electron. So that means we have one reaction, one relationship. We change this guy, and we want to see how these two would change. So that's the whole idea of PC, PE. Those C would be, in this case, these two species. So before we talk about the system itself, at higher electron activity, would you expect more of this guy or this one? Conceptually speaking. Fe2 plus. So more electron, that means more of the reduced species. So you have more electron to reduce Fe3 plus to go for Fe2 plus. And this is basically a spoiler, but this is basically what we get. At a lower PE, which means higher electron activity, so P is always opposite, is minus log, so we get more of the reduced species, and then more oxidized on the other side. Very similar to pH diagram. More protonated on this side, deprotonated on this side. So, because obviously we have more H plus here. So let's continue with this. This is the first relationship. The second relationship is basically a closed system. So we're allowed to use mass balance on the iron species. What is the total Fe? No, what is the description? It's 10 to the minus 4 equal to Exactly. So both of them are Fe. So basically we have Fe2 plus Fe3 plus, and both of them are a part of the mass balance. And we know this is basically 10 to the minus 4, which is given. And now what we did for example, complexation or acid base was, this was the core relationship. What we did was converting one of the species concentration to the other one. And we rely on this one. And let's say we go with Fe2 plus. So we need to convert Fe3 plus to Fe2 plus, and this is what is basically what we need. So based on relationship 1, Fe2 plus stays the same, but Fe3 plus would be Fe2 plus times the electron at the standard condition, or to the electron activity. So this is basically a constant. Just keep in mind this value is a constant. Or rearranging a little bit, Fe2 plus is total Fe divided by 1 plus E to the activity of electron, or the concentration of electron. So now the rest would be pretty straightforward. We have the concentration of one species, which is a function of what we are changing, in this case electron, and constant. And we know how, once we find the activity or concentration of this guy, we know how to calculate the concentration of the other guy using relationship 1. So, and using Excel, we just change the activity of electron. So we basically change it at each concentration of electron, or PE. So basically it's minus log of that. We calculate Fe2 plus using relationship 2. Then Fe3 plus by relationship 1. So it would be a very simple spreadsheet. So I'm not going to show that spreadsheet. Just keep in mind this would be eventually what you're getting. And this is basically the more oxidized species on this side, and then more reduced here. And as you see, everything is changing significantly. So if you remember for PCPH diagram, this point had a meaning, which was pKa, for example. Is it the same here? Something that is useful related to Fe2 plus, Fe3 plus? So it's PE0, exactly, 13 point something. So it seems it's also giving us some good information. So that means if we had a redox pair with lower PE0, then this would be something like here, like this one, for example. But don't rely on this much, because as you see, as it gets more complicated, then that value, especially when we involve acid base, that doesn't provide a good information as like PCPH diagram. So for now, because this system was relatively simple, we can just say, oh, that's a PE. Okay, so this was the simplest case for redox, just one redox, already standard. None of the species in the redox are reacting with anything else. So now the next part would be adding one layer of complexity. So we have one redox, but that redox species, one of them, is also a part of acid base. So here we have a solution that contains 5 10 to the minus 4 total Cl, any Cl, any Cl4. Distributed among 3 species. So these are the 3. And before even we look at the other information, we can tell whether going from here to here or here to here is a redox by only looking at the oxidation state. If oxidation state doesn't change, that means you're dealing with acid base. If it changes, that means you're dealing with redox. But here the information is given. So PE0 for HOCl, Cl minus, so that means we have one redox there. And then we have pKa for HOCl. So out of these 3, which one is more involved in terms of reaction? Which one is the heart? Which participates in both acid-base and redox reactions? HOCl. So HOCl is basically the one species that could go either way. That could be a part of acid-base, could be consumed, or it could be a part of redox. So obviously this example is pH dependent. And we're doing it for 2 different pH, 4 and 10. See, acidic pH, basic pH. So the diagram for this case would be HOCl as the main species. So we get, it could go to Cl minus through a redox. It could go to, OCl minus as through an acid base. So basically we get this line acid base and this line redox. So before we do the calculation, let's say Cl minus is something bad, something that we really want to avoid, but we can't avoid HOCl in the system. So in that case, we can basically involve HOCl in this reaction to convert it to OCl minus as much as we could, to preserve it in OCl minus as much as we could. So we minimize the concentration of Cl, or we minimize the involvement of HOCl in this reaction. So that means high pH or low pH. So just focus on this part. Low pH, so you get more of this guy. So you have more of this to go to Cl minus. High pH. So if we have high pH, most of this would be in the form of OCl minus. So not much to form Cl minus. So we're expecting at pH 10 to see lower concentration of Cl minus. So that's, again, without doing the qualitatively speaking. So that's actually a very interesting approach to get rid of some of the species that we really don't want. So let's say you're forming HOCl in your company. You want to transport it to a different location, but you don't want that to go in the form of Cl because that's very corrosive. So what you do is adjust the pH. At the point of delivery, you can basically go backward and then get to OCl minus. So something like that. This is very simple, but then as you see, this could be way more involved. It gives us more flexibility to play with it. So in terms of the reaction, as always, this is no surprise that HOCl, one acid-base reaction, OCl minus plus H plus. And then this is Ka, describes this reaction, where we have also HOCl going to Cl minus, and we know how to balance this reaction. I'm going to skip that part. So this would be 2 electron plus, or so it would be plus hydrogen plus 2 electron. We can't use E0 for this reaction. We have to make it in the standard form. So that means producing only one electron. And now we can use E0 for this reaction. So now that we have the reaction, we know we have some relationship between the species. So the first thing is, what are the species? What do we have? The simplest form, even simpler than that. What's that? Yep, H plus OH minus, always. We have always those species. So we got H plus OH minus, and now what else? Let's say we're on the biggest one, HOCl, OCl minus, Cl minus. What's missing? Exactly. So electron is a species. So as I mentioned, this is something that we should get used to, like to see electron also. So 2, 4, 6 species. Obviously, we have already 6 relationship. Mass balance. I'm skipping that. 2 relationship here. So we have enough, and we have Kw also for water. So we have enough. So let's focus on some of the main equations that we're going to use, and specifically the mass balance. What's the total Cl, the value that we have? And what's the species? Exactly, so all the 3. Again, that diagram is also telling me that these are all the Cl. HOCl, OCl minus, and then Cl minus. And now, because HOCl was basically the bridge between the other 2, we can convert other concentration to HOCl. So converting this guy to HOCl, that means we have to deal with that redox reaction, this one to this one. It would be just a simple acid base. So now the next part would be to get rid of these 2, mentioning something like HOCl. So we can start with Ka to get rid of OCl minus. So this would be OCl minus, H plus, and then HOCl. Therefore, OCl minus would be basically Ka over H plus HOCl. And then to get rid of Cl minus, just relying on this specific reaction. So that means the standard reaction has to be written. HOCl half, then H plus half, and then electron, and then Cl minus half. So therefore we get Cl minus to be HOCl, H plus, electron to the power of 2, and then E0 to the power of 2. So now we just need to insert these 2 into the mass balance. So this would be 3 and 2 into 1. Then the total Cl would be HOCl plus Ka or rearranging it a little bit, then it would be HOCl. So I think now would be pretty straightforward. We change E0, but it seems this relationship is pH dependent as well. So as we talked about, but we have a fixed amount of H. So this is either pH 4 or 7. So this is also fixed then. So we get HOCl as a function of the activity of electron. Once we calculate this, we can go backward, calculate this one, and calculate this one. Very straightforward. So what we get would be, we first calculate HOCl from 4, and this would be at each PE, or the activity of electron. Then OCl minus and Cl minus from 3 and 2. And as I mentioned, this is basically pH dependent. And if we calculate that in Excel, then we get something like this. So it seems what we talked about, it's correct. So, but then it has to be like pH 10. So as you see here, OCl, the concentration extend less in terms of the electron activity compared to here, that extends up to here. And the Excel should be pretty straightforward, but we can quickly look at the spreadsheet. This would be something like this, that we have OCl minus HOCl, from the more involved formula that takes into account also the pH value. So as you see, this is pH dependent. This is for pH 4, but the next one is for pH 10, as you see. So this is the pH value. And once we have this, these two would be pretty straightforward, and then the rest would be basically the minus log of the individual cell. So this example, what it did was involving redox with one acid base. So the next example would be coexistence of two systems that don't participate in the reactions of the individuals. So what it means is that we have the same system in example 1. So basically we have HOCl, OCl minus, and Cl minus. So that's in the system. At the same time, we have also Fe2 plus, Fe3 plus in the system as well. But Fe2 plus and Fe3 plus, it seems they could complex with hydroxide. And we're going to solve this for a fixed pH of 7. So it seems Fe2 plus could complex with hydroxide up to 3 molecules. And the same thing for also Fe3 plus. And still no precipitation, so this is a closed system. So the first thing is to do the diagram. again, as always, this would be a very good starting point. We have Fe2 plus, Fe3 plus in one hand. And what this describes is basically E0 of Fe2 plus, Fe3 plus. So now we know each of these guys can also participate in a complexation reaction. So in the previous chapter, I normally go with like this arrow, but as you know, this is basically also an equilibrium. So let's just go with equilibrium. With hydroxide as the complexing agent, and we know that proceeds up to 4. So FeOH plus and FeOH2, FeOH3 minus, and FeOH4, 2 minus. And the, what's that? Oh, 3. Yeah, you're right. Somehow. Okay, that's even better. So up to 3. So the one for this one, the equilibrium constant would be beta 1, but for Fe2 plus. And this is beta 2 for Fe2 plus. This is beta 3 for Fe2 plus. So we know Fe3 plus also has the same kind of complexation profile with the same hydroxide. So this would be FeOH2 plus this time, FeOH2 plus, and FeOH3 with 0 charge. And the constant would be B1 for Fe3 plus, B2 for Fe3 plus, and then B3 for Fe3 plus. Any other reaction that involves iron? Potentially, this could also precipitate. This could precipitate, but for this example, no more. So this is all the speciation for iron. But it seems in parallel, we have also speciation for HOCl. So before we proceed with that, let's just mark this. This is basically a redox. And this is complexation. So it seems in parallel, we have that HOCl system. This would be E0 of HOCl, Cl minus. And then here would be Ka to form OCl minus. And in terms of the reaction, similarly, this would be acid-base. And this would be the redox. So again, 2 independent systems. You don't see this often, but just to show that they could coexist. And as you see, both of this diagram are pH dependent. This one because it has an acid-base profile. This one because the complexing agent is an acid-base. It has an acid-base characteristics also. How many mass balance we have based on the information that is given? 2, right? 1 from example 1. So we have 2 independent mass balance. So this is basically the total Cl from example 1. And this would be total Fe, which is 10 to the minus 4 that is given here. So there is nothing new here. We talked about this branch at the beginning of this lecture. We know how to independently look at these two branches. Complexation, beta value is given, pretty straightforward based on the first two lectures of chapter 3. And this one we just solved. So it would be coexistence of many parameters at the same time. So they're not interconnected. So for example, Fe is not reacting with any of the species involved in the other branch. In reality, or maybe in the exam, they also might coexist, for example, Fe with Cl. So then the two branches are connected together, and then it would be a little bit more involved. So now that they are independent, we could proceed with, for example, total Fe. We know this would be Fe2 plus Fe3 plus, I'm not going to write all the 6 complexes, just say 6 complexes, which you know what are those 6, 3 here and 3 here. So the next part is to convert all the concentration to Fe2 plus. Again, the same common practice that we used to do. Every single concentration to Fe2 plus. Or first to Fe3 plus and then to Fe2 plus. So that's, for example, for these species. You can convert it to Fe3 plus and then Fe3 plus to Fe2 plus. So to make it simple, to make it one variable at a time kind of approach. So in page 2, we show how to go from Fe2 plus and Fe3 plus. So Fe3 plus is basically E0 of Fe2 plus Fe3 plus times Fe2 plus divided by the activity of electron. So this would be the first relationship. So the next part would be looking at Fe2 plus complexes. We know how to do it based on chapter 3. So we show that we can make it like generalized, so we can expand it to all the 3. So Fe2 plus I hydroxide forms FeOH I. The charge would be 2 minus I. Right? This is, we can expand it to get out to all of this. I1, 2, and 3. And because it's written in the form of the standard designation for beta, beta I is describing this equilibrium for this specific notation that we use. So beta I of Fe2 plus would be just the product FeOH I 2 minus I divided by Fe2 plus times hydroxide to the power of I. So since we don't want to repeat what we had before, just trying to use a general notation because it would just repeat itself. So now that we have this relationship, we can expand it for 1, 2, 3, and for each individual of these 3, convert that concentration to Fe2 plus. So just rearranging a little bit. So then for FeOHI 2 minus I, this would be beta I Fe2 plus times Fe2 plus, what we need, and then OH minus I. And you saw that rhythmic behavior also in chapter 3, that sometimes OH, then OH to the power of 2 to the power of 3. Let's just represent that. So now we broke down all the 3 complexes for Fe2 plus. We could do the same thing for Fe3 plus. But then it converts everything to Fe3 plus, but we're interested to know about Fe2 plus. So then it would be then Fe3 plus to Fe2 plus using relationship 1. So and if we do that and then combine everything together, then would be all into total Fe, then we would get something like this one. Fe2 plus itself, then Fe3 plus in the form of Fe2 plus. Then all the complexes. So that's the first complex for Fe2 plus, then the second complex for Fe2 plus. Then the third one for Fe2 plus. So now the rest would be basically complexes of Fe3 plus. So plus beta 1 of Fe3 plus. But now this time, instead of Fe3 plus, we have to replace it by Fe2 plus times the redox parameters. And now this times the complexing agent. So this would be basically Fe3 plus. And then you see that pattern of that I, which in this case is 1. And now we just need to expand it for 3 more. See if I can cheat a little bit. So the next one would be beta 2 of Fe3 plus. And then times the concentration, so it didn't work. To the power of 2 here, and then the last one would be beta 1 Fe3 plus. Sorry, this should be beta 3. And then the rest would be So as you see, this relationship, we only have something that we're changing, something that is fixed, something that is a variable, and then something that we're calculating. So we just need to rearrange it a little bit to have a clear or better FE2 plus expression that we're going to use. So this would be total Fe divided by 1 plus a 0 of electron and plus beta 1 Fe2 OH minus plus 2 OH minus to the power of 2, and then the rest. So now we have that nice, relatively clean expression of Fe2 plus as a function of constant and as a function of something that is fixed and something that we're changing. So once we have Fe2 plus, then Fe3 plus using equation 1 would be pretty straightforward. But for HOCl system, would be the same as example 1. Again, because this is not interfering with the Fe system. So if we go to the Excel file, we see that this is basically this time, I guess we have roughly 24 different columns representing almost 12-ish species. So the most involved probably is this Fe2 plus. And as you see in the formula, it takes into account so many different constants and also something that is changing, which is the concentration of electron. Once we have that, Fe3 plus would be very straightforward. The rest of the complexation is similar to chapter 3. HOCl, again, from example 1, exactly the same because the two systems are not interfering. Otherwise, it would be more complicated or would be more involved, HOCl. So basically, we calculate for the key elements. And this HOCl is HOCl, Fe2 plus or Fe3 plus, it doesn't matter, would be the key element, and the rest of the speciation would be calculated based on what we have here. And tons of other constant for redox, complexation, no precipitation in this case, but also acid base. And eventually we get something like this, that this time, as I mentioned, this lines that it's basically crossing, the two lines are crossing, this might not have the same good information, straight information as we have for like the very simple example. And this is, again, you can basically decide, for example, at pH as PE of 10, what is the major species. So this is Cl minus from the HOCl system, and it is FeOH2 plus from the Fe system. So that's sort of analysis that we had it also before. Just keep in mind, this is for a fixed pH. So as you see, this could be a 3D kind of diagram that you also in one hand changing the pH. But here for the sake of simplicity, we made it 2D. And these are the total Fe kind of species. These are basically the total Cl. So again, two independent, not interfering with each other. But to quickly check, more reduced species on the left, more oxidized on the right. To just quickly check whether this was correct. So Fe2 plus and Fe3 plus, as you see, this is the concentration of Fe2 plus, and this is the concentration of Fe3 plus. So that follows that kind of trend of Fe2 plus on the left side of Fe3 plus. Any question? Okay, pretty straightforward. It's just combining what we've learned. And now the last example is basically pretty much a combination of whatever we've learned in this course in terms of speciation. So just decoding what is given, it seems we have complexation with OH, we have complexation with HS, but this is beta 2, keep in mind, so we're ignoring beta 1. We have some redox for lead also. We have some precipitation, and we have a acid-base reaction for a biproduct acid. So this is what we're expecting in our diagram. So the question is asking about lead, which is a big environmental concern. We have reactions, all the reactions provided. Initially, we have total lead of 10 to the minus 6 molar. So that might be less because we might have precipitation. And then a solution pH is 4. It's also exposed to a gas phase. So it seems there's also a gas phase reaction here, but HPM is giving in the question itself. So 10 to the minus 3 H2S. So, and then the range for PE is given 15 to 45. So the first thing is doing the diagram. So as you see, this is probably the most involved you could see in terms of including different reactions. You might get a different sub-branch. For example, for complexation, you might get, instead of 2 and 1 for each, you might get 5 for each and 3 different complexing agents. But in terms of the branches, this would be the most you could get. So what's the core here? Which one should be the core that is involved in the most reactions? Which one? Why 2 plus? Why not 4 plus? Yep. Complexation is with 2 plus. There's no complexation information about 4 plus. What about precipitation? Also with 2 plus. So the heart of this diagram would be PB2 plus. So we get PB2 plus. What is the first branch that you're interested to work with? Complexation branch. So complexation, the easiest is, first one is with hydroxide. How many? So with 1, so PbOH plus, and this is beta 1 of hydroxide. What else? So still on the complexation. So again, before we just had one arrow, but just keep in mind it's always a equilibrium. So this would be with HS minus and then PB just 1 HS. What's the charge then? It's actually 2. Yeah. So the charge is 0. It's neutral. And this would be beta 2 of HS. Just keep that in mind always. That might be a little bit confusing. We're skipping PB1, like PB with 1 HS. We're done with complexation. So this would be all complexation. So what's next then? Before that. One before, redux. So still, yeah. Staying with PB2, so PB2 could also be involved in the redux, E0, PB2 plus. Sorry, PB4 plus. And no further reaction for PB4 plus. It could, but in this specific example, no more reaction with that. So this would be the branch for redox. So what's next then? Yeah, potential precipitation. So the next one would be some potential precipitation. What's the agent and what's S2 minus. So forming PBS in the form of solid, and then KSP is basically describing it. So this would be our precipitation. What else? Okay, so let's say you want to do gas equilibrium. With what species? But we still don't have H2S on the map. But right now we don't have H2S. So easier to work with acid base first. So S2 that is on the map right now with Ka2 could be HS minus. HS minus now can form Ka1, can form H2S by Ka1. And now we can basically, now that we have H2S, it's not a closed system, it's an open system. So this is basically with HPM dictates this equilibrium, we can form H2S gas. So this would be acid base, and this would be any other reaction that we've learned in the course that is not here? What's that? So everything it seems is here, acid base chapter 2, gas equilibrium chapter 2, these two chapter 3, and now this is chapter 4. So if you remember, like the very first lecture, we talked about this course to be sort of a water chemistry rather than environmental chemistry, because we had this diagram of water in contact with gas, also in contact with the solid phase. And this is basically a very good example. So this is what we have. Eventually, the heart is in the water phase. Eventually, we have a gas phase, we have a solid phase, but all in contact with the liquid phase. And that's how we dictate the speciation in the liquid phase. So that's another reason that I was insisting this kind of diagram would be very, very useful. And it just organizes your mind in terms of where the species might go. So at some point we need to do mass balance. At least that was our approach for a system that might have precipitation, going with no precipitation, with precipitation kind of idea. The last two lectures of chapter 3. So we need to do at some point total mass balance for lead. What are the species that contains lead? What is the total lead expression then? So Pb2 plus this one, okay. Okay, these two. Okay, so 4. So that's it. We don't include this because this is obviously not in the system, it's leaving the system. And none of these guys, they don't contain lead. They dictate or they change the distribution of the lead containing species, but none contain lead. So that's how they're impacting the distribution, not the total amount. So then this would be, the total would be Pb2 plus. We are 2. Then Pb3 plus. Then complex of Pb hydroxide. 4 plus, you're right. Thank you. And then PbHS2. And it would be very easy to convert everything, all the 3 concentration to Pb2 plus concentration. So this is what we had in the previous lecture. Just the complexation route, the redox route. Eventually we could have, because we need, for a no precipitation scenario, we need to rely on this relationship. So this reaction is already not standard. This is basically the standard format. So we need to just keep that in mind. So what we were given was the standard format already there. So E0 is Pb4 plus electron, and then Pb2 plus. So now we have the expression for Pb4 plus as a function of Pb2 plus. So that's the first expression, replacement of one of the species. The rest would be also very straightforward. So beta 1 of hydroxide would give us Pb hydroxide plus divided by Pb2 plus times hydroxide. So then Pb hydroxide plus would be a function of constant, also Pb2 plus that we're interested. Then the next one, beta 2 of HS is equal to PbHS2, then Pb2 plus HS minus to the power of 2. PbHS2 then would be beta 2 of HS, Pb2 plus, and HS minus to the power of 2. So as you see, this is a scenario that we have no precipitation and precipitation, so both. We know how to deal with it. First, the no precipitation scenario. Is NP 1, 2, 3 into total PB expression. Then we get PB of no precipitation would be equal to total PB divided by 1 plus the activity of electron to the power of 2, then the other two expression. So in addition to this guy, we also need with precipitation scenario. So and that's basically give us the maximum concentration for PB2+. Which would be KSP divided by the precipitating agent, Se2 minus to the power of 2. Just Y2 because it's we need two of them to form 1 mole of complex, or 1 mole of precipitate. So one quick question. This guy, for example, the concentration of this one, it's not electron dependent. So do you expect to see, like, when it comes to PC-pH diagram, to see like straight line? It is pH dependent, but we fix the pH. Exactly. So that's electron dependent. So even though there's no electron directly in this expression, this one already is electron dependent. Also, this hydroxide, this could be more involved. This hydroxide might be, in other scenarios, might be a part of a species that is involved in the redox reaction. So indirectly, the electron activity is impacting eventually the impact of the other species as well. So this is for PB2+. We know many of this expression, specifically this one and this one, is also a function of the acid base of H2S. And this is an open system. We know how to deal with that. So for acid base, and it's an open system. Now the concentration of H2S is fixed, and that's basically the partial pressure of H2S divided by the Henry's constant in the form of HPM. We know HS minus then is equal to Ka1 H2S and then dividing it by H plus. And S2 minus Ka2 HS minus, just a simple acid base, H plus. So this is fixed, right? Because it's a function of the partial pressure. and then HPM. Can we say this is also fixed? This one. So this is fixed because these two are fixed. pH is also fixed. Unlike the PC-pH diagram, here H plus is fixed. So this one is also fixed. The same for this one. And if you look at these three, you see that this is always fixed. So you have a constant feed of H2S, which is translating into HS minus and S2 minus. Even though it's being precipitated, it's been removed from the system because the partial pressure is the same, it's always coming to the system. A very complex system could be when you have the partial pressure is also changing, which is the case when it comes to gas treatment. But in this case, we have a fresh flow of H2S. You shouldn't be in contact with it, but that's coming in. The concentration is not changing or it's not significant, so we can deal with this. But in reality, if you're dealing with air treatment from H2S, then this would be a completely different ballgame. So now that we have speciation for all the species, then it would be pretty straightforward. The approach would be at each concentration of the electron. Then we calculate acid base. As we talked about, this is not actually needed. This is always constant. So it's just for the sake of the pipeline. Then once we have acid base, we calculate Pb2 plus no precipitation. We calculate Pb2 plus max. This is a common approach when it comes to potential precipitation. We take the minimum. And then once we have the minimum, that's basically the concentration of Pb2 plus. And then once we have that, we can calculate the other species based on all the relationship we had in the previous page. So if we take all of them into the Excel file, then it would be something like this. The activity of electron is changing. The first thing we calculate for acid base. As I mentioned, this is basically fixed because H2S is fixed and pH is fixed. And pH is actually 4 in this case. So was it 4 also? Yeah, pH was 4. So then no precipitation. Pb2 plus no precipitation, as you see, is a function of so many beta values and the rest. Then Pb2 plus max, just a function of Ksp and the precipitating agent's concentration. Okay, need to check the note. So there shouldn't be. And then once we have that, the minimum is basically the minimum between the two would be the Pb2 plus. Once we have Pb2 plus, a redox relationship between Pb2 plus and 4 plus. So that is a function of E and E0. Then this is a complexation reaction, a function of beta. This is also beta, and this is basically the total. We can also look at the QSP and comparing it with Ksp to see whether we have is undersaturated, oversaturated. So as you see, we start with precipitation. And then as we increase the concentration, we get more coming to the system. So it would be no precipitation. So let's go back to the figure. So let's just make sure that this was, oops, this shouldn't be 2. So just Pb2 plus and this 2 minus this 1. Doesn't change much, but. So now this is basically the profile that you get precipitation. And you get here no precipitation. Why no precipitation here? So this line, the black line, is the total PB. Is it the same value as we had initially? So it's not, right? It's 10 to the minus 6. Wait. How much we had? Yeah, we had 10 to the minus 6. So no precipitation at that point. So, yep. Yep. Yeah. So it seems we can remove lead from the system at a fixed pH by lowering the activity of electron, the total lead. And when we look at the diagram, we see that when we lower the activity of electron, the P of activity. So that means when we increase the concentration of electron, what we're doing is this ratio is leaning towards more like Pb2+. And once we form more Pb2+, there's bigger opportunity for Pb to go out from the system in form of precipitation. So we're intentionally moving this reaction leaning towards Pb2+, because eventually that goes out in the form of Pb2+. That's why we expect of more of Pb2+ at higher concentration of electron, so more potential precipitation. So again, a very simple trick to get rid of precipitation. So let's say if your electron activity is fixed, then you have another route to involve hydroxide, for example, because in that case, you can increase or reduce the pH to eventually impact these two routes. So it's a competition between going this way or going this way. You need more of the precipitating agent. That means higher pH. At higher pH, then bigger chance to get rid of that. So you have, again, another approach to get rid of lead from your system by either playing with pH or by either playing with the electron activity. But as I mentioned, pH might be a little bit more tricky because when you have higher pH, so then you're also involving Pb2+ still in the solution. So it's not as straightforward as electron. So it would be a very delicate, nice game between how we can design a system for a specific application. In this case, to get rid of lead through precipitation, at least. So this was probably the most involved, wrapping up the whole course so far by involving all the different reactions that could possibly happen. So what we did in our diagram, we had complexation branch before. We had sort of a precipitation branch. What we added this time was basically just the redox branch also. So that's how basically one ion could be involved in the environmental systems. Any question? So if not, in the next lecture, we'll be focusing on PEPH diagram, extremely useful. It's called like sort of a Pourbaix diagram. We're going to make that. And then that would be very useful to distinguish what we have in the system at a given pH and PE.